Center view. All right, so welcome to the course on complexity in global systems science. We're living in a complex world, and this world has always been challenged by all sorts of problems, threats to societies, such as, volcano outbreaks or hurricanes or tsunamis, or also perhaps asteroid crashing the Earth. These were singular localized events, basically. And now we're living in a much more complex world, which is largely networked and interactive, and there are additional and maybe even bigger problems that result from them. Systemic instabilities could cause financial, economic, and debt crisis. Oh, I think I have not even opened it. It works, right? I'm not. Social and political instabilities, environmental and climate change, organized crime, cybercrime, or the quick spreading of emerging diseases. And I don't even want to say when I produced that slide, basically a long time ago, somehow we had that on the radar screen. Unfortunately, societies were still not very well prepared. Then, of course, terrorism is to mention, mass migration, conflicts. Perhaps I should take this picture instead. Hopefully, it will not escalate. But the main problem we're faced with is actually another one, which is lack of sustainability. So we're basically consuming more resources than we should, and that's going to be a problem on the long run for planet Earth and for humanity altogether. Given all these problems, two colleagues that I've admired a lot have made pretty clear statements. I wouldn't have been so courageous to formulate it this way. Sandy Pentland said our financial, transportation, health systems are broken. And Geoffrey Best, with whom I've published some papers, he was also the president of the Santa Fe Institute for some time, one of the complex system science centers. He said we're seeing an extraordinary phase of our current political and economic system. So I'm still allowed to quote people, so I chose to do that rather than making my own comments. Who agrees, by the way? That we have, we are seeing systemic failures, basically.
Haven't we always?
That is debatable. Was it always that bad?
No.
If I remember times back, in the 70s, 80s, I think, and there was the Cold War, which is, I think, right? At that time was still the Cold War until '89, basically. But that was the main concern, and otherwise life was easy and happy, I don't remember these times very well. Anyway, so how could we understand those kind of problems? And that brings us to complexity science. And what is this about? I'm starting with some examples of complex systems. So turbulent fluids or gases would be examples. Traffic flows, large supply chains, social, political, economic, and ecological systems, financial markets, group dynamics, and crowd behavior, to mention just a few examples. But we need to distinguish clearly between complicated and complex systems. This is a complicated system. It contains many parts. If we would have to fix it, we probably ran into a problem. But those parts play a very well-defined role. They're well-controllable, typically. And that's why you consider a car to be a safe thing, I guess. And you feel comfortable controlling it, be able to do that. Traffic flows, on the other hand, that means the interaction of many cars, are an example of complex systems. And no matter how hard the individual driver tries to control it, he or she will sooner or later run into a traffic jam. It's kind of an unavoidable thing that results from the interactions of many cars. You cannot prevent it, even though you want it. I will pay some attention to this in the course of the course. Complex systems are a daunting class of problems. They concern systems with large numbers of interacting elements or components. That could be individuals, could be companies, cars, even countries. We would have nonlinear or network interactions between those different elements. And in many cases, there is rich system behavior that does not have anything to do with poverty or not. This just means that those systems could show many different kinds of behavior, as we know it from nature and society and markets, in fact. These systems are dynamic rather than static. They're often probabilistic rather than deterministic. In many cases, they show surprising or even paradoxical system behavior. For example, slower is faster effects. We'll come back to this when we talk about pedestrians and traffics. These systems are often hardly predictable, often seemingly uncontrollable, and they challenge our common way of thinking. And in a sense, unfortunately, they're almost everywhere around us. So they're a nightmare for decision makers, politicians, managers, and everyone else. I guess we've seen that during the pandemic management, right? Here is just an illustration of this faster is slower effect. If pedestrians are running towards the exit and very pushy, then they could block the door for some time, and basically this slows down the evacuation process. It's just one of many kind of paradoxical, unexpected, surprising behaviors. Nonlinear interactions, I said, is an important feature of those complex systems where basically many system elements adapt to others in time and they'll adapt again. Everyone adapts to everyone else in many cases, to some extent at least. So elements are influenced by their environment, but at the same time, they influence their environment. And so there's emergence. The environment changes also its properties. And that's what we call emergent behavior. We could, for example, have unresponsive system behavior, as you can see over here, right? So some manager is changing the culture, say in a company, doesn't work, so he's pushing harder and harder, and nothing happens, and suddenly everything changes, but not necessarily in the way that was intended. So there would be tipping points at which there would be regime shifts, as we say. For example, sudden public opinion changes, right? Pro versus anti-war mood, public smoking bans, Swiss banking secrecy, I guess that's back to be a subject again. Car sales and so on. Network interactions are, of course, ubiquitous. There are feedback loops, in some cases, certainly virtuosi. That's spiral out of control. There could be cascading effects, there could be unwanted side effects, and that's quite typical. I think there is a famous example, I'm not from India, where they paid a certain amount of money for a snake to be killed. There were too many snakes, basically. And if I remember well, that just caused that people started to grow snakes at home, basically to make money with that. But there have been other countries too. I mean, it's just really one of a million examples of this kind where people may have good intentions, but it turns out that it just makes things worse. Now I'm playing a little movie for you that we have produced ourselves. All right. Any questions or comments? Yes. That was shown in the beginning, which were the equations, and so we're talking about a logistic equation. The same system, but the discrete one is a discretization of the other one, right? So it's discrete in time rather than continuous. That is the main difference. And as you can see over here in the beginning, there's basically one equilibrium value, and then above a certain critical value, that is called Q4, you would find an iterative behavior. It jumps between two different solutions, and here 4, 8, and eventually you have the chaotic dynamics. And these are the kind of systems that were investigated in great detail a couple of decades ago, when people got excited about the discovery of chaotic systems. The remarkable thing over here is that those chaotic systems are based on deterministic dynamics. So it's unpredictable, or sometimes, even though you would think it should be predictable. Yes? Some of those systems have that feature, not all of them. But the scale-free feature often occurs at tipping points, which are the points which we are most interested in, where system behavior changes kind of abruptly. And there you have that's the self-organized critical systems have a tendency to move towards that tipping point and basically be at that point all the time. And then they do have, in fact, that scale-free behavior. It's like, I mean, for everyone else who doesn't know what you're talking about, there's this famous example of basically dropping sand on a table, and then the heap grows, and from time to time you will have an avalanche of sand. Those avalanches will have different sizes. The sizes are parallel distributed. So sometimes they're small, sometimes they're big, sometimes they're even very big, and that statistics is not compatible with the bell curve, with Gaussian distribution that we often expect from systems. So basically, extreme events are a lot more frequent than we would expect according to our intuition, which is often based on the bell curve. Are more frequent. No, extreme events are more frequent. That makes them so dangerous. You know, the avalanches could be big, and that could basically really create big trouble. You have the same thing in stock markets. And you can very well imagine that if you have these large fluctuations, the stock market may crash. And that's not a good thing from the point of view of most people. All right, and it turns out if you start from a certain point in the parameter space, and some systems have several parameters determining the dynamics of the system, and then you would sometimes get an equilibrium outcome and sometimes get chaotic or oscillatory or whatever. And this is represented by different colors over here, so you can see that a close by point in the parameter space could lead to very different outcomes. So you cannot interpolate, basically. And these systems can look beautiful, but in a sense, they're still very messy. These are idealized systems though, right? I would not claim that real systems behave this way, but those models still help us to see what can happen, even in well-defined and even in deterministic systems. All right, but what we can conclude from these examples is that the limits of predictability, so assume you change the 10th digit after the comma. After some time, if you have this deterministic chaos, you would find totally different dynamics. And this is also known from realities, for example, from weather forecasts. Right? For some time, you can predict, but beyond a certain critical time period, it doesn't work anymore in most areas of the world. And then we talk about the butterfly effect, right? A very minor change could really have a big difference, make a big difference after some time. It's really hard to imagine, I admit that, to imagine that a butterfly by flapping its wings could actually change, make the difference between nice weather and a stormy weather weeks later. But the mathematics of those systems suggest that in principle, there's a grain of truth in that. So the butterfly effect is just an illustration of that. The slightest changes could make a difference later on. And a big difference, that's the point. And there are also limits of control. So I already mentioned big changes may have small effects, no or adverse effects. Sometimes, however, small changes may have big effects. So causes and effects are not proportional to each other. There could be irreducible randomness. Delays may cause instabilities. There might be regime shifts, as we discussed. And now let's go a step further towards global system science. Now, global system science can be read in two ways: as global systems science or as global system science. And both ways of reading it make sense. Surely, what global system science wants to do is it wants to deal with real or realistic systems, perhaps global systems even. And not just those logistic maps that we talked about before, right? These very theoretical, hypothetical kind of systems. And so here is a paper that I've authored on that subject, and I'm just reading you the abstract because I think it contains a couple of important things. Today, strongly connected global networks have produced highly interdependent systems that we do not understand and cannot control well. These systems are vulnerable to failure at all scales, posing serious threats to society, even when external shocks are absent. So small changes have big effects. As the complexity and interaction strengths in our network world increase, man-made systems can become unstable, creating uncontrollable situations even when decision makers are well-skilled, have all data and technology at their disposal, and do their best to make these systems manageable. A fundamental redesign is needed. Global system science might create the required knowledge and paradigm shift in thinking. And so the hope is that in this course, we learn a bit about those systems and how they behave and what that implies for the way of managing them. Because I do think that knowledge is important, not only in economics and politics, it also is important actually in physics, chemistry, biology, medicine, and many more areas. So strongly coupled systems and complex systems behave in a fundamentally different way. They often show faster dynamics, increased frequency of extreme events. Self-organization dominates the system dynamics rather than what you can control from the outside. Emergent and counterintuitive system behaviors may come about. Predictability goes down, external control as well, and there's larger vulnerability. And here you see the comparison of a power law or scale-free distribution that we discussed before with the bell curve, the normal distribution. You can see it makes a big difference. Those large or extreme events are more frequent. And that is what makes it so dangerous. No, it's higher. The green curve is higher. The probability, the frequency is higher.
Oh, okay, so and the measures.
So of course, networking is good. It has many advantages, but also it can have unwanted side effects, in particular cascading effects. And those cascading effects, if combined with probabilistic behavior, could really make it very difficult to reconstruct the underlying system dynamics. And in fact, the combination or interplay of risk and complexity can create uncertainty. And do you have an idea of a system where this applies? Huh? Absolutely, right? So that is a person who got COVID and might infect other people in the neighborhood, but only with a certain probability, right? And with a delay, then we have exactly this kind of situation. And as we've seen, it can get quite messy. And a good system to illustrate the system dynamics is this one. If you have a rainy day at home, it's a nice experiment. That's one as we've seen, for example, in the case of the financial crisis, Lehman Brothers went bankrupt, and that triggered the bankruptcy of hundreds of other banks, and losses actually were in the billions and trillions eventually. Multiple times higher, I think at least 100, if not 1,000 times higher than if you would have paid for Lehman Brothers. And now it has really become a worldwide systemic problem. You know, how to heal that system? Can it be healed at all within the current system? It's not COVID, I hope. So some people think this collapse of the financial market was somehow related with the increasing density of the banking network. So banks got ever more connected, ever more exchanges and contracts and so on. And
that actually triggers such a big event is the fact that in this case, for example, there is one big hub, right? And the fact that distribution, it's like we have a big hub and then a big one. And so when one fails, then that needs to catastrophic. Instead, if you have several, like it's also with the pandemic, right? We have the, that's why this time we have a pandemic and all the viruses that we have to go. populations were more distributed cities, and we have like population density, like densely populated areas, and it's easier to just get it out of stuff.
Yes, if there's dense interaction network, then in fact the risk of cascading effects is bigger. As we know from that example of the table tennis balls that I showed you, which is representing basically chain reactions as we have them like in a nuclear cascading effect, right? Either atomic bomb or nuclear power station. And there is a threshold, a critical threshold. If you exceed it, then basically the process is kind of unstoppable. And this is in fact how it works, you know, how you detonate an atomic bomb that two subcritical systems are brought into direct neighborhood. Well, that depends on the network, of course. But a lot of social or economic networks do have that scale-free nature in a degree. That's when you go to the tipping point, I assume. Are you referring to the too big to fail thing? Okay, so we're moving on with network interdependencies because in many cases now we have not only networks that can show cascading effects, but we have networks of networks or multi-level networks, networks of different kinds, such as electrical networks, communication networks, financial networks, social networks, and all of that is interlinked. And so problems can spread from one network to the next, and in many cases makes networks or systems a lot more vulnerable. A typical case is a blackout. People are unfortunately talking a lot about it recently. So if that happens, it does have impacts also on other systems, such as traffic systems. Traffic lights would be off. There would be terrible congestion. Public transport would be down. You would not have your light bulbs. Instead, you would use candles. With a certain percentage, there would be fires. The firefighters would have to come. They may not be able to do that because the streets are blocked. Water would have to be boiled because you wouldn't get fresh water. But without electricity, how do you do that, right? So basically, one thing triggers the next problem. And so there are often secondary and tertiary disasters, as you can see over here. So for example, an earthquake could cause a volcanic eruption, could cause a landslide, or it could also cause floodings, tsunamis, for example. And worst comes to worst, unfortunately. But nevertheless, these systems have typical features. If you analyze many disasters, you would see that one thing triggers the next thing, but you can say what triggers what. And you can basically construct a causality network and thereby predict in what order you would see what kind of problems. And that allows you to prepare for it. So you can take proactive measures to stop the cascading effect. And you want to stop that as early as possible because that would really reduce the damage potentially dramatically. So when such a situation occurs, all is about stopping the cascading effect. Yeah? Yeah? We don't know where the tipping point is, right? So we know there's likely a tipping point, but we don't know where. And once we see it, it may be too late, right? That's the big problem. It's not entirely true, in fact, because when you come close to the tipping point, you would have at least two phenomena in many cases. One of them is critical fluctuations. That means you would see that the system has larger variations. You often see that in the financial markets too, before you have a big collapse. It goes up and down a lot more than usual. When that happens, you know, okay, well, you're most likely approaching a tipping point. Yeah.
Could it also be that and produce something, but nobody?
That can happen. Yeah. I mean, certainly it's useful to have these indicators like the critical fluctuations, right? Because you want to do something to avoid disaster. But there are so many things that you need to do on this planet, to create a better world, and you want to use your resources in a targeted way, in the most effective way. And so if you assess it wrongly, of what is the bigger problem and how big it is and when it's going to be and when your action is going to be effective, then yeah, there's also a danger of investing the wrong amount at the wrong time, too much or too little, too early, too late, whatever. So that's it's a difficult problem.
I think sometimes these systems are so vulnerable. And we tend to build vulnerable systems because they're very efficient. For example, as a society working together and being interdependent, we're more efficient. We're also more vulnerable to anything. Now we don't know how the batteries are together. Not we don't know that we depend on so many things and so many others. With that, and so we're going to now, for example, there's no electricity because we're not prepared because we're safe before, we're dependent, we're efficient, but with efficiency comes with vulnerability. So it's hard to like when that tipping point is approaching, we should start to we have our efficiency. It's like, for example, in the financial crisis, right? Then we should change completely the network of who owns whose shares. It's like the network of interdependency should be like broken, so that establish some firewalls or something.
So one other way, I mean, that's exactly what I was trying to point out before when I said it's not always wise to go to the limit, And the most efficient point could be the most unstable, in fact. This is where systems often start to collapse or become ineffective, whatever. But the goal, of course, is of this course to spread some hope that to some extent we could simulate those systems and their behaviors, and this way understand potential behaviors and also under what conditions they will happen. Right. So I think the situation is not entirely hopeless. Anyway, we cannot live without, I guess. But I'd like to encourage you basically, to learn these methods and to apply them to those kind of systems where sudden shifts in system behavior are expected. All right, so in the coming lectures, I will talk about pedestrian crowd and evacuation dynamics. I'll talk about traffic flows and how to reduce them. I will talk about evolutionary game theory, and this is about modeling cooperation in particular. And I will talk about diseases and disasters. And today, for the rest of the time that we have, I will give you an introduction to agent-based modeling of complex systems. So here's some elements of modeling complex systems. First of all, in many cases, these are social systems, but in fact, in many cases, they're even more complicated or complex than that. They're techno, social, economic, environmental systems. Just as a motivation, because I was employed as a sociologist here at ETH, I have a physics background. Now you understand why I showed you the slide, because the father of sociology, Auguste Comte, he was proposing to develop social physics to understand society. And he thought it was the queen of all sciences, because it would be a lot more complicated or even complex than physical systems. That were kind of his inspiration source for formalizing what's going on in society. And agent-based modeling is actually trying to do that. Now, of course, physics is in a way simple, even though who is physicist in the room? Yeah, I guess you may not agree, or perhaps you do. It's I mean, it's complicated enough, right? for every one, there is a problem that is beyond the complication that is tractable.
Yeah, I think there's definitely emergence, right? So there are what we can explain society by some emergent dynamics that are simple.
In fact, we've learned a lot from physics about complex systems. And a lot of complex systems scientists were physicists. And as you can see over here, I am showing you actually the elliptic cycle, elliptic orbit that planets are taking around the sun, in comparison with a mathematical description that works kind of equally well, but has a lot more parameters in it, So before, when they had a geocentric worldview, the movement of the planets was seen like this. So they're epicycles. And in order to describe them, you have to overlay cyclical movements, many of them. This is like a Fourier decomposition, let's say. But that, of course, is a much easier description. So if you change the perspective, then things get very simple. And the question is, would such a thing also be possible in sociology or in sciences that are trying to make sense of how society behaves? And then there are two traditions, I would say. Some scientists are trying to come up with a very detailed description. And others would try to simplify and boil things down to what they call the essence, to abstract the system, to simplify it as much as possible, but not more than that. And that's kind of in art, the art of science, complexity science, if you want. It's clear if you consider more parameters and more terms in your descriptive model, you could fit data better. I mean, you could imagine it also as a Taylor expansion or some other infinite series expansion, right? So you have, if you want to have an exact reproduction of the data, you need an infinite number of terms and parameters in many cases. But then the physicists would still say, okay, let's focus on the greatest orders of magnitude and treat a large number of terms as small corrections to that overall dynamics that we're interested in. Exactly. So if you take a model with many parameters, you would fit the data better. But if you then take another data set, that model may not perform so well. And in many cases, a model with less parameters would often be better in predicting the behavior of those systems, these other systems. So this is called overfitting in a sense, right? So if you, for example, fit the society of Switzerland with big data sets, and then they want to predict how Singaporeans behave, you know, you would probably not find the perfect match. And this is because of overfitting, right? In Singapore, we have a somewhat different culture and also different temperature, and that has implications. And so those societies are differently organized, different political systems, and so on. But we don't want to have a model that you always have to fit to every single system. You want to have a model that you can fit to one system and then it can predict something about another system. This is predictive power. So how powerful a model is in terms of prediction is the thing that we're mostly interested in. Right? And so here's a comparison between underfitting, overfitting, and just the right degree of detail. And in fact, many people working in AI have also realized that this is an issue. And there is best complexity of the model. And in order to get there, for example, you would apply pruning or some kind of methods like that. Now, in many cases, you want to understand system behavior from the behavior and the interactions of the system components. In the case of society, we're talking about, for example, coordination. That was not well coordinated. Coordination, cooperation, group identity, social norms, social structures, social change, conflicts, and so on. But the assumptions that you make shouldn't already imply the outcome. You want to understand this as an emergent collective behavior of interacting system components, which you would give some elementary features as little as possible, as few as possible. Just as much as you need in order to understand that kind of behavior, right? So among those elementary facts are births and deaths and reproduction, individuals need resources, food and drinks, competition is there, and so on, memory, mobility, communication. But in many cases, you would not need all those features. to understand a certain problem such as cooperation or conflict. If you want to learn something about agent-based modeling and how to do that, there's also a chapter in my book on social self-organization, but of course a lot more papers and reviews such as this one over here. And the essence is that system components are represented by agents. Those could be simplified representations of individuals, of companies, of cars, whatever. And so you would give those agents attributes, just those that are needed to produce some collective outcome that you want to understand. There are different ways of model specification. There are rule-based approaches, kind of if, then, else, or decision trees, yeah. That is predictive. And there are also equation-based models. So here, some of the equations that we will come back to later on, corresponding to the intelligent driver model. And you could also have a mixed specification of agents. And then there would typically be parameters in those equations or in those rules, and those would have to be chosen in a way that would allow you to fit the system behavior. That is called calibration, right? So for example, if you have traffic flows, and these are different vehicles moving along the road in the course of time, and you have these trajectories, and you want to be able to reproduce those trajectories as good as possible, and need to adjust the parameters like B0, S0, T, AB in those equations, right? Often this is done with a least square method, minimizing the overall square error. And the idea is then often, it will not only allow you to calibrate your own model, but you could also use it in order to eliminate competing models. Right, so in traffic flow modeling, there were eventually, I guess, more than 100 car following models. So each team had their own. And each of them was convinced they had the best one. And then Peter Wagner and his team basically said, okay, let's now decide which is the best model. And they took a data set, a car following data set, and they're fitting different models to this data set, and that was the outcome. In a sense, it was surprising because it shows, okay, there is a best model, but it's not clearly the best. I mean, the second best is not that much worse. And at different intersections is not always the same model which is the best, right? So in fact, the surprising outcome was this was not the way to eliminate all the other. Are you trying to say something? No, because you raised. But perhaps even more important than the calibration step is the validation step. And so you have to test your calibrated model with another data set. And only then you will figure out how well it actually can predict the behavior of that other data set. And that gives you an idea about the validity of the model. It's a good or a bad model. In many cases, you could have a well-fitting model, well-calibrated model that would be very bad at predicting other data sets. The least you would do is you would take a data set and split it into 2 data sets and use one half to calibrate and the other half to validate. Even better would it be to take one data set and then challenge your calibrated model with another data set. So for example, we would calibrate pedestrian flow dynamics for central station in Zurich, and then we would challenge it with a data set from Washington, DC, or from, I don't know, Moscow, or whatever comes to mind, Rome.
That's very interesting because some things like how general the model. If you want to be that general, right?
Yeah, I mean, this is important in order to answer the question, do you really understand the essence of that system? And otherwise, you know, we need to look further on for better models, right? So the thing about AI is AI has often a lot of parameters, right? So it's good at fitting more or less any kind of data set. But then the question is how good is it at predicting other kind of situations? And that's not always that successful. We'll take also an approach that is aiming to understand what is going on in the system, in contrast to a black box approach, which is often considered to be the situation for neural networks or deep learning. Doesn't mean that it wouldn't be useful to use both methods. You know, for example, you could use a model-based approach and then learn the parameters with a neural network, right? Rather than applying least squared method. All right. So some particular properties of complex systems. Multi-stability. I already indicated that complex systems could have rich system behavior. That means they could show different kinds of outcomes. And here just some of the traffic patterns that you could find along a freeway. Many different kinds of congestion. And in fact, we'll go into more detail in another lecture. Right? There are points in the parameter space where you could have different outcomes depending on what happened previously. Whether you had a small perturbation in traffic flow or a large perturbation, for example. It turns out that, however, the method of those phase diagrams is useful to distinguish different kinds of models. So among the 100 car following models that I mentioned, some of them show this phase diagram, and some others would have other phase diagrams. And then you would basically have to figure out what phase diagram do we find in reality in the empirical data. Then you could basically identify a class of models that is consistent with the empirical data. So that is much more selective with regard to the suitable models to understand traffic dynamics as compared to only doing the calibration that or also validation I mentioned before. So it's an additional method to select among competing models. And in fact, this paper is talking about that at length. So here, for example, you see some other phase diagrams you could have for other kinds of models, and what kind of phase diagram you get basically depends on certain kinds of parameters that we'll also talk about in more detail later on. Right? So quite a large number of different settings that you can find as phase diagrams. And for all of those phase diagrams, there would be mathematical models that claim to be traffic models. And only then the empirical data decide which is the right class of models. There might still be 20 models in that class, right? In that case, you would often just take the simplest because it's helping you to understand what's going on, even if it doesn't have the very best fit. It may not be that much worse than the best fitting model that may have 10 more parameters, but model with less parameters tells you more. And you find these phase diagrams also in systems that describe cooperation, right? Here is an example of the situation of the environment, the ecosystem, on two sides of a border. That's the border between Haiti and the Dominican Republic. Here, deforestation, here you still have a lot of trees. So how do you get from here to there, basically, or how do you keep this? Well, this is a matter of collective social dynamics. People often talk about tragedies of the commons, that the cooperative behavior wouldn't be stable, and then you end up in a situation that you don't want to happen, like environmental destruction. People have come up with all sorts of mechanisms, social and biological and other mechanisms, that would be able to stabilize cooperation. And so here we have a system of 4 possible different behaviors: cooperation, uncooperative behavior, cooperation and punishment of uncooperative behavior, and defective behavior and uncooperative behavior, and punishing other defectors. So again, in the beginning, we have 25% of each of these strategies randomly distributed, so fair chance. In the end, you only stay with 2 of them, the defectors and the moralists. These are the cooperators that punish the defectors. The others disappear. But the majority in the end is the cooperators who punish defectors. While defection, corresponding to the tragedy of the commons, would be only a small share of people. Right? Now, the interesting point is, if you would have all those people interact with all the other people, you would just get defection, D, rat, all of them. However, as they're here interacting only with their neighbors and they're imitating the most successful behavior of their neighbors, you get a very different outcome. And in fact, this also very much depends on the parameters of the model. These are phase diagrams, as you can see, and it doesn't have to end up like this, what we just saw, red and green. But you could also have this, for example, red and blue, maybe. Or this, ending up with red and yellow, maybe. Or with red. There's also this method of the overlay phase diagram. So producing phase diagram takes a long time. You have to make, say, 100 simulations for each point in the phase space. And you have more than 2 parameters, say 5 parameters or 10, then you can simulate for a very long time. Over here, we overlay space over a 2-dimensional parameter space. And so you basically see how system behavior changes as you change parameters. And that can help you to get a quick overview, and then you can still make more detailed investigations later on. Yes.
So at each point in the phase diagram, and then you summarize those. But I guess
so here you make a simulation in space over time, but in each of these points, the parameters are slightly different.
Right. So the question is, why is it that for a given combination of parameters,
oh yeah, absolutely. So because there's some randomness in the simulations, you don't always get the same outcome. And so in order to have some meaningful statements, you need to look at the sample of simulations. And
I guess the question is like, what is a meaningful summarizing statistic? Because the results of the samples. But like, you know, depending on the distribution, I'll summarize the results of the science.
That's a very good question. And overall, the standard is that it would not only show averages, but also standard deviations. And maybe even box plots or other representations. So if it turns out that you have bimodal distributions and an average may not be meaningful at all, then you would need to find another visual representation of your results. Right? So if you figure out that for a certain parameter combination, you find qualitatively very different results, then you need to look into this in a lot more detail, and averaging may not make sense. But you might have a situation like what I said before, that things may depend on the size of the perturbation, for example, right? We speak of history dependence also. Yeah, here. So small perturbations, large perturbations. And so we would always have free traffic flow over here for small perturbations, but for large perturbations, we would have the pin localized cluster, which is this thing. Okay, tipping points. We've been talking about this already in the beginning. When it came to the ice shelves and so on. So in many environmental systems, but not only over there, here, for example, also in physical system like a magnetic material, we could have hysteresis. I mean, it's history dependence, the thing that I just mentioned before. And so if you come along here, then the system changes like this. If you go back, then it changes like this. So it's not a unique curve that goes up and down. And as I said, this is found for spin models, but also spin models are often being used for opinion formation. model. Here just a few papers that we could choose to talk about. And we do have this also in environmental systems. And here's in social systems, when it comes to social norms and revolutions, for example. So we'll now change the parameters in that simulation. And what you see is that there's a sudden jump, basically, in the system behavior. This is what we call a revolution, you know. So there's a mathematics that allows us to understand revolutions. We'll come back to this later on as well. Fluctuations and noise are also a typical thing. We've made some experiments in the lab with certain incentive structures, and what we basically found is certain kind of typical behaviors, and we could come up with a mathematical model that predicted 96% of all decisions in a deterministic way. That was an amazing accuracy. However, this is the typical outcome of an experimental session. This is what the deterministic model predicted, very different. However, when we then added some noise to the deterministic model, we got this thing, which looked much more similar to what we get in the experimental session. So that means if you're interested in understanding the system behavior, it may not be a good thing to have an accurate deterministic model for the individual. Adding noise could make things more realistic, and the reason for this is that the system we're looking here over here is unstable. Flipping the behavior of one individual would cause a cascading effect in the system. So if you don't consider errors or random changes, you could not understand the system behavior. Of course, errors would have a significant effect on the overall outcome. Right? So here is an example. This is the beginning, and here 2 deviations, and then basically you get this kind of development over time and a very different outcome with yourself. We'll have similar examples later on in the game theory session. And here is the paper. Also, there are many different dynamic system behaviors. Having an equilibrium solution that doesn't change anymore sometime is not necessarily the normal case, for sure the most boring case from a scientific point of view. You would have cycles, you could have torus, you could have a strange attractor. This is kinematic dynamics. And these are still all attractors, right? That means if you basically start close by, your trajectory would go into that attracting solution. But in many cases also, you would have instability. And we know that actually from the weather. The underlying equations are fluid dynamic equations that are known to show turbulent dynamics for certain parameter combinations. And a similar phenomenon is somehow the deterministic chaos. So we're talking about the butterfly effect. In fact, these kind of models have also been developed as a simplified, perhaps oversimplified model of weather dynamics. So you see If you start with a very similar value, for some time, the system will behave similarly, but eventually then they will behave very differently. I could also figure that out if you move along those trajectories. So there is sensitivity in many cases. In a sense, we could distinguish systems into two classes of systems, stable ones, which tend to go into equilibrium and thereby behave somehow in a predictable way. And that means reasonably small deviations would not have a big effect. What the individual does doesn't matter. You know, it feels like, oh, we cannot change the system. But there are other situations, and these are when you're getting to a tipping point of the system, where things get unstable. And then the system is likely to get out of control, but in unpredictable ways, and everyone could make a difference. While before you tried to change the world and couldn't do it, in that situation, suddenly, a single individual could change the world fundamentally. Because the butterfly effect comes. And this is what you want to know. Do you have a stable system or do you have an unstable system? Where are the dangerous areas of the parameter space that you perhaps want to avoid, or perhaps you want to get there in order to change the system to a better system? Right? For this, you make a sensitivity analysis. And over here, you can see slight changes in parameters which cause very different predictions about the future development. This is a prediction of COVID cases. Well, we've seen how difficult that is, how big the uncertainty is, but it's not the only system. Look at predictions of world population. Look at peak oil, even climate change. You know, there's unfortunately not certainty about the future development. But there is instability. The sensitivity analysis can be done with a particular mathematical instruments called Taylor's inequality coefficient. Now, unfortunately, many problems in the world result from systemic instabilities. And these are crowd disasters. Nobody wants them to happen. These are basically unstable supply chains. And even managers would have difficulties to do the right thing in that so-called beer game, which is a supply chain game. We do also find that in our economy, booms and recessions just show that kind of instability is typically considered to be undesirable. And also crime comes in waves, and that also shows instability. Right? Tragedies of the commons. I would think nobody really wants them to happen, but they happen because the desirable behavior, which is cooperative behavior, is unstable. And so it tends to erode. And we end up with those tragedies. Conflict also, in many cases, are not intended. Think of all the divorces. They were probably not planned at the time of marriage, I guess. And unfortunately, those instabilities can also occur in relationships between countries. And revolutions are obviously another example of unstable. Network effects are obviously important, but the implication is that there would not only be intended effects, in many cases there would also be unwanted or undesired side effects, there would be feedback effects potentially, there could be cascading effects. And we know that, for example, from electricity grids, I think we'll make it a bit faster. course, we will also come back to this. And a similar cascading dynamics can be found when it comes to the spreading of diseases. And here, it's the connection density, as we already discussed before, that really matters. So if there's too much interaction between people, and basically the pandemic would get out of control. That's why we did have those distancing rules and wearing masks and lockdowns and so on, basically to get on this side of the graph. And cooperation is another example. It could spread or disappear. We'll come back to that too.
For example, diversity, so the general field, and then the connections to the neighbors. We're very diverse, and we have a very extended random field. It's less prone to developing this large avalanches.
Simply said, you could say, in a homogeneous system where every component behaves the same, if one of those components has a problem, all of the components have a problem. There's nothing that would stop it. So if you have a diverse system or heterogeneous system, you know, with some nodes that would be affected, and others would still stay stable. And that is, of course, very important for the resilience of the system, of society in particular. And that's why it's good to have different cultures and different organizations of society, right? I mean, humanity is facing difficult times, but you know, all those cultures, I think, are important to get through those times well, in particular by supporting each other.
For example, we said before that the tendency towards evolution and difference. But always evolution tends towards consumables. It's like a battery in a way that also consumes a difference eventually.
I would say that what the economy does, or at least say that what companies do, they try to, in many cases, to come up with large numbers of the same product. And so that reduces potentially diversity. You know, the strategy is basically say what is the problem, and then you apply optimization, you identify the best solution. And so of course that solution affects most profits, I guess. And then you would scale it up and roll it out globally, that one solution. And that, of course, would undermine diversity and would undermine resilience. Evolution, on the other hand, works in a different way. Evolution is fueled by diversity. It's the variance that drives the improvement of fitness over time. So zero variance means no evolution, no improvement in that evolutionary system. And diversity is a benefit towards improvement of the system.
We should go and say that this increase of diversity is a product maybe of also depending on the stage of evolution of a certain system. Like it's on a self-organizing sort of stage. For example, a non-equilibrium system, when in the beginning, when it's like when the non-equilibrium is higher, let's say, and then, for example, usually these complex systems are the ones that are have a source code. Right, so there's force in the system, and then it requires that complex behavior in those mechanisms. So if it's just a system that is then with no source, it just tends towards equilibrium. Sorry, I come from a physics background, sorry. So there's a space, early phase maybe, which the system so there's always maximum production.
Yeah, I mean, you can look at it in two ways. One way is to look at averages and how they change over time, and there you basically see the increase in fitness over time is proportional to the variance of solutions. And fitness increases and variance increases too. And interestingly enough, there's a paper that I've written about that, and there could be at least two different dynamics. One, I think, had a parabolic evolution in time, the other one was exponential. So I found that very funny. Perhaps you could switch between those two dynamics, if that makes sense. The other perspective is to look at a spatial temporal dynamics. And what often matters for evolution is to have niches, right? Because if you mutate a good solution, it might initially be a bad solution that would not survive. It was not protected by a niche. It takes basically time for it to get to a majority that would allow to compete with the species that are already around. So if you eliminate all the niches, then that evolution cannot happen. A lot of the better solutions that would come up over time with niches would just not happen. And this is important also for our economic system, because innovation shares a lot of commonality with evolution. So if you don't allow for niches for innovation, and we don't allow for different cultures, also, we could actually dramatically affect the innovation on this planet. So it's good to have different systems, right? And it's important to realize. Okay, and then I'd like to highlight distributed control. So it's important to realize that society cannot be steered like a car. And this has also to do with that graph over here. We do have an exponential increase in processing power. That's a nice thing to have. But data volume grows even faster than that. So basically, there's a lot of data we'll never process again. We could call that dark data, and that percentage of dark data is increasing all the time. So the implication of this is, when we process data, we need to know what data to process in what way. I think it will never be able to automate it completely. It will always need scientific domain knowledge to decide what is the best way to process data. Yeah. It's about reproducible sharing. But then there's also systemic complexity, and that actually grows even faster than exponential with the networking in the system. It grows basically factorially. And so that complexity curve even overtakes the data volume. And paradoxically, that means even though we have more data than ever and better technology than ever, we tend to lose control as we try to control the world in a centralized way. So we need to have a different control approach. Fortunately, there is one, namely distributed control. And that would basically use the principle of self-organization in those complex systems to reach the system behavior that we'd like to see, just by specifying the right kind of interactions in the system. And we'll learn a lot more about that in the coming lectures. So, using complexity as an ally rather than seeing it as an enemy. You just need to learn how to use complexity for yourself. And you need to accept to give up some control in order to let good things happen. However, you know, if you have the wrong kinds of interactions, self-optimization could produce outcomes that are undesirable, such as those stop-and-go waves. We'll also come back to this. But by slightly changing the interactions, that annoying stop-and-go wave that we're now seeing could actually be dissolved. By slightly changing the acceleration and deceleration behavior with an adaptive cruise control system that responds to neighboring cars, in fact, mainly to the car in front, in a slightly different way. What we're doing now does not require a control center. It just requires mechanism design. That means a slight change of the interaction mechanism such that an unstable system dynamics would be changed into a stable system dynamics. And you'll see that this traffic jam will disappear. For this, it would be enough to measure the distance and relative velocity to the car ahead with a radar or laser sensor, and to change the acceleration and deceleration. So real-time feedback is basically the solution, and with the Internet of Things, we can now make that self-optimization happen. We can make the invisible hand work 300 years after Adam Smith came up with that concept. Now, of course, there's also learning. So for those of you who love machine learning, of course, that is also important because our agents in many cases represent humans or companies, and those are systems that learn. And that could be modeled with a neural network, learning. It would give those agents some ability to sense the environment in which they are, and also to respond to that sensory input and learn how to respond more efficiently. And basically, the goal is to come up with something we call swarm behavior. And I'm not the only fan of that. Actually, here you can see the tweet sent by the Nobel Prize Committee when Giorgio Parisi earned the Physics Nobel Prize last time. And he had also worked not only about statistical physics, but also about the flocking behavior in birds and how this collective dynamics comes about. Because there is no leading bird, there is no king or queen bird that tells everyone else what to do. Everyone is just responding to some neighbors around and adapting. Everyone is adapting, and that creates a wonderful, amazing collective living system. It's not required to understand this kind of dynamics. I mean, there's some birds that have a lead bird, like audience, I think, which have this one formation. But there, interesting enough, is also one king or queen, but the position of the leading bird is being changed over time. It's very tiring, and after some time, somebody else takes over. It's actually a way to reduce the aerodynamic friction of flying that formation. All right, so now about the course schedule. Basically, I will give a few talks. I mentioned already the subjects that I'll talk about, and then basically it's your turn. We'll have a lot of slots for student presentations. The length of your talk will depend on the number of presentations we have all together. So the less presentations, the more time. It's actually a good thing. We'll know that in a couple of weeks' time. You'll choose a paper to report about. We'll put it into a web page so we can see who chooses what subject and what time slot. Would be between 2 and 4 people, I guess, in one time slot. So we'll also make sure there's time for discussion. You should make sure to explain the question that the paper wants to address, the approach, the methodology, the results, and then discussion and outlook. You could also go a step further and add your own additional results or considerations that have not been addressed by the paper. So critical reflection is very welcome. We don't just have to reproduce what other people said, but you will have to explain things well to all of us. And that will be graded. I think it's 3 credit points to earn for that. And here are a book and a collection of articles that you might select from, but you don't have to. I mean, I'm happy to see stuff that I haven't seen before. Just if you select a paper that is not in our collection, it would be good to ask for our feedback. I typically recommend to choose a paper which has either quite a few citations, say around 100 citations or more, or has been, if it's a preprint, that's also okay, but I would suggest to choose a preprint from a team that is well established. So we can assume it has the high level of quality that we expect over here. It needs to have, or some other quality criteria like publication, a high impact journal, like if it was published in 2022, then it certainly doesn't have a lot of citations, but if it was published in Nature Science, it would probably have been peer reviewed very critically, and the quality would hopefully be high. That doesn't mean that we would agree with the paper. I mean, we'll have a controversial discussion, I hope, about each of these papers, interesting discussions, and hopefully learn a lot. And there's some more literature, but it's not what we necessarily are restricted to. Okay.